Okay, good morning, everyone, and thank to the organizer to giving me the opportunity to present to you my work. So, as Roman said, I'm now in Leiden, but the work I'm going to present to you today is actually one of the last work I've done during my PhD thesis. And here are the collaborators of this work, and among which my two former supervisors. So I'm going to compare peaches and oranges, and if you wonder why, I'm going to explain in a minute. First, let's start with a schema that you already seen throughout the week and earlier today. So these are the four main phases to form a solar mass star, and so I'm not going into the details. What is interesting is from a chemical point of view, actually, because from the earlier stages to the latest one, what we see is an increase in the molecular complexity. And one of the big astrochemical questions we can have is to understand whether the molecules that were formed at the early stages and that could be considered as prebiotic species survived along all of this journey and leading to the apparition of life on Earth. So this is one of the questions. In other words, to understand if there is inheritance from the early phases to the latest one, or if there is some reprocessing along the way, and how much. So during my thesis and in this talk, I'm focusing on the protostellar stages. This is the most, this is one important stages because this is where most complex molecules are formed. And in fact, this leads to a relatively rich chemistry. Not all protostars have the same chemical content. In fact, we observe two chemically distinct types of solar mass protostars. So on the one hand, you have hot corinos. You already heard about it today. It's dense, hot, and compact regions, enriched in what we call interstellar complex organic molecules, such as methanol, dimethyl ether, and many more. And on the total opposite of the spectrum, we have warm carbon chain chemistry sources, so WCCC sources. These sources have their inner regions, that is deficient in atoms, but they show an enrichment in the long carbon chain and rings on the most outer part of the envelope. One of the questions is, of course, why is there such chemical diversity? Our main guess for now is that everything is happening at the previous stages, so at the prestellar phase, where the ice mantle composition could vary. And why would the ice composition vary? We have, I will present two main hypotheses. The first one is the difference of time scale of prestellar core phase. So very quickly, here is a schema of what could happen in the case of a short prestellar core phase. The carbon atom doesn't have time to lock onto the CO molecule and will freeze out alone on the ice mantle. And after hydrogenation processes, we would have methane-rich ice. If the prestellar core phase is long enough, then CO molecule can have time to form and will freeze out onto the surface, onto the ice mantle, leading to a methanol-rich ice. And once we move from the prestellar core phase to the protostellar phase, temperature increase and molecules can dissolve. In case of a methane-rich ice, methane dissolves around 25 Kelvin and will react in the gas phase to form longer carbon chains. And in that case, we would have a WCCC sources. On the other hand, if methanol-rich ice dissolve, then methanol is in the gas phase and other complex molecules, and in that case, we have a hot corona phase. However, this interpretation has been recently challenged by models performed by Akawa and et al., where they could reproduce hot corinos and hybrids, which are protostars having both a hot corino and a WCCC zone, but they could not reproduce pure WCCC, so they could not recreate this lack of icons at the center of the protostar. The second hypothesis is the role of environmental factors, so the variation of density, temperature, and illumination or irradiation during the prestellar core phase. I show here an example in terms of different illumination. So in the case of uniform illumination, the photons are going to break the CO molecule. So again, we have only the carbon atom that will freeze out onto the surface of the grains and leading to the methane-rich ice. If the core is more shielded, then the CO molecule survives and will freeze out onto the surface, leading to a methanol-rich ice. And in case of non-uniform elimination, we would have then a mixed composition. So in the first case of uniform elimination, it would favor WCCC protostars, while in the case of no elimination, we would have a hot core reno. And there are recent studies that showed that for lower density, lower temperature, and higher irradiation, we would have actually more likely a WCCC source. So during my PhD thesis, and what I'm going to show you here, we wanted to understand if the environment affects the chemical composition of protostars, and if yes, how. So for that, the idea is to study solar mass protostars chemical composition following two considerations. First, we need to do it at small scale because to avoid possible external composition coming from the molecular cloud in which the sources are still embedded, or even possible PDR if the environment is sufficiently illuminated. And of course, we have to study protostars in different environments. And this was the goal of peaches and oranges. So Orange is Orion Alma New Generation Survey. It's a survey that targeted 19 protostars along the OMC23 filament that is located in Orion A. Orion is considered as a dense protocluster with high mass stars, and in fact, you can see that the filament is bounded by 3 different H2 regions, so it's quite highly UV illuminated. And before so the goal of my thesis was to understand how many hot core renos are in this filament. On the other hand, the Perseus Alma chemistry survey surveyed 50 solar mass protostars in the Perseus molecular cloud complex, which is considered as a much looser protocluster, and it's devoid of massive stars. And a study led by Young showed that hot core renos in that region are actually quite abundant, with almost 60% of the target. So the two surveys were actually made to be compared because we probed the same spatial resolution, we reached the same sensitivity more or less, and we have the same spectral setup. Before oranges, actually, there were already 3 hot core renos detected in the filament, 2 of which are intermediate mass protostars, and 1 hot core reno, 1 solar mass protostar. And here in the cyan, I show all of the protostars that we investigated. And to probe hot core renos, we chose to target methanol, which is the most simplest and most abundant icon found in hot core renos. So we detected methanol in 5 out of the 19 sources. So I show here the in red shaded colors, gray and black contours, the continuum emission of ALMA of the sources at 1 millimeter ALMA observation, on which is overlaid in green the moment zero of one of the methanol transitions, the one at 45 Kelvin. For some of the sources, the outflow direction was actually known, so I show them by with the blue arrows. You can see that the methanol emission is relatively concentrated towards the center of the protostars. It can also be relatively extended following the outflow emission because here we have a low upper energy level transition, and sometimes we don't resolve the emission of methanol. Here are the different transitions we detected, and actually for one of the sources, we could use also the 18 isotopolog methanol, which is very useful to derive accurate column densities. And because of the large upper energy level that we performed the non-LT LVG analysis to derive the gas physical properties where methanol is emitted. And we found that in all of these 5 sources, the gas is relatively dense, hot, and compact. So we have discovered 5 new hot core renos in the OMC23 filament. So in terms of statistics, we arrived to percentage of less than 30% of hot core renos in Orion, in the Orion region. And here in the oranges are the position of the hot core renos. So you can see that they are more or less scattered throughout the filament. There is no particular trend on the position of hot core renos and with the filament. So from there, we could say that oranges appears to be different than peaches. However, there are two main caveats that needs to be taken into account. The first is, of course, the sample size. We could investigate only 19 protostars in the case of oranges, so it led to relatively large statistical error. So we had 26% of hot Corino plus or minus 23. So in the end, we need further more statistics to firmly conclude. Another important caveat that is possible is the dust. There is a recent studies led by Mathilde Simon that showed that at millimeter wavelength, if the dust is optically thick enough, it can completely obscure the presence of a hot Corino. So to check if dust was playing a major role in detecting hot Corinos in oranges, we compared the velocity integrated emission of one of the most intense methanol line as a function of dust optical depth that we derived in a previous continuum work. The 5 hot Corinos are shown by field rectangles. The other sources have a lower limit, of course. And we didn't see any correlation or anti-correlation, because if the dust would actually play a major role, then we would expect that the hot Corinos are actually the sources with the lowest dust optical depth, which is not the case here. However, as you can see, there are 4 sources for which the dust optical depth could be high enough. So we cannot rule out the fact that these sources could actually be undetected hot Corinos. We will have a part of the answer, because actually there are ongoing GVLA observations that are, we observe now one of these sources at 25 gigahertz, so where the dust is supposedly optically thin, and we targeted methanol to try to understand if methanol was hidden in the dust or not. So we will have a part of the answer soon, so stay tuned for that. So here are the main take-home messages. So we detected 5 new hot Corinos in the OMC23 firmament. Hot Corino seems to be relatively scarce compared to Perseus in Orion. And the environment could be the culprit for this chemical variation. However, we need to, in order to firmly conclude, we need to improve the statistics, and we need to address the possible caveats of the dust. And I would like to spend the last time to explain to you what I'm doing now. So I am in Leiden University in the group of Serenavity. And in the same way as I was interested in the effect on environment on the variation of protostar chemical diversity, I'm also interested of what happens at a much larger scale, so at the scale of a galaxy, and how the chemistry varies from one AGN galaxy or a more starburst one. This is why I was very glad to join the MOPEX group, where the goal is to compare these two galaxies. So there is a composite AGN starburst galaxy, NGC 1068, and a pure starburst galaxy, NGC 253. And my first work actually, the NGC 253 is actually part of the ALMA large program Alchemy. So we did, it is an unbiased survey from 80 gigahertz to more than 300 gigahertz of this galaxy. So there is a lot of lines detected. And my first work will be on sulfur-bearing species. I show a moment 0 of the H2S in the central molecular zone of NGC 253. So if you are interested in nearby galaxies or sulfur-bearing species, stay tuned. And with that, I thank you for your attention.